I am Anil Kumar. Welcome to my series on rational functions. In this video, we will understand how to describe characteristics of a rational function and also how to sketch a graph of a rational function. The question here is, describe and sketch f of x equals to 5x minus 10 divided by x plus 2. Now I'll find few parameters which are listed here, that is y-intercept, x-intercept, vertical asymptotes, horizontal asymptotes. Then we'll figure out behavior near the asymptotes and behavior interval, where f of x is positive or negative, interval for slope to be positive or negative, increasing or decreasing slope, right? So all these characteristics we'll discuss. So let's begin with the function itself. F of x equals to 5x minus 10 divided by x plus 2. We can factor 5 in the numerator, so we get 5x minus 2 over x plus 2. Now this equation helps us better to understand the situation. When we say y-intercept, it means what? Y-intercept is when x equals to 0. So basically, you need to find the value of the function when x equals to 0. Well, I can substitute it right there. What I get here is minus 10 by 2, right? Which is equal to minus 5. So I get the y-intercept as minus 5. Now to find the x-intercept, which is when the value of the function is 0, we actually solve the equation that 0 equals to the function itself, right? So 0 equals to the function itself. Now that is possible when the numerator is 0. So we can use the factored form, which is 5x minus 2 equals to 0, and that leads to x equals to 2. Correct? So x-intercept is at x equals to 2. Now the vertical asymptotes. We do not have any common factor between numerator and denominator. So that will be denominator being 0. That is to say, we can equate x plus 2 equals to 0, and we get the value x equals to minus 2 as the vertical asymptote for the given function. Horizontal asymptote. The degree of numerator and denominator is same, and therefore the horizontal asymptote is equal to the ratio of the leading coefficients, which is 5 over 1. So the horizontal asymptote here is y equals to 5 over 1 or y equals to 5. So these are few very important characteristics which we have found within few minutes. Let's try to understand their significance on a plane. So we got here a few very important parameters. I'll make a rough sketch of this. And then later we'll discuss their behavior, mainly the behavior near the asymptotes. So what we figured out is that we have y-intercept at minus 5. Let's say this is minus 5 for us. So that is the y-intercept, minus 5. X-intercept is at 2, right? So let's say this is 2 for us, and this is x-intercept for us. Vertical asymptote is at x equals to minus 2. So we can draw a vertical asymptote right there. Then we have a horizontal asymptote at x equals to 5. So at x equals to 5, let me draw a horizontal asymptote. Rather, y equals to 5, sorry. So y equals to 5 is your horizontal asymptote. So we kind of get a framework here. Now looking into the function, which is, and all these points, we kind of get an idea how the graph will really look like, correct? So what we can do here to sketch a rough graph, since we have x equals to minus 2 value here, let's calculate the value of the function at some more points. One of them is x equals to minus 3. So if I substitute minus 3 here in my equation, what do I get? I get 5 times minus 3 minus 10 over minus 3 plus 2. So which is minus 25, 15 and 10, right? Minus 25 over minus 1, which is 25. So that means at minus 3, which is 1 unit on this side, we have a point which is right here. Now this point is kind of important. It gives you an idea of the graph itself. Here is a vertical asymptote which you cannot cross. Here is a horizontal asymptote which in this case will not be crossed. And therefore, looking at these points, we can actually sketch the graph of the function, right? So that becomes the graph of the function. Connecting these points, we get another part of this curve. All right, this is a vertical asymptote. It will go down. Do you see that part? So kind of with these values, we already have the sketch for the given function. Now, let's describe the behavior near the asymptotes. So when we talk about behavior near the asymptotes, we are more worried about the vertical asymptote. That is x equals to minus 2, right? So if I substitute a value which is slightly more than minus 2, which is on the right side, that is minus 1.9, then what happens? So if I substitute this value here, I get 5 times minus 1.9 minus 2 over minus 1.9 plus 2. So what we notice here is that the numerator here is negative, right? However, the denominator is positive. So these two combinations, when you divide negative by positive, we get a negative result. That means that the behavior near the asymptote is kind of towards negative infinity. Do you see that? That is the part, right? So we can say that when you're approaching from the right side, then you're approaching towards the negative infinity, right? So that arrow indicates when x approaches minus 2 from the right side means positive value. In that case, y approaches negative infinity. Is that clear to you? Now to find the behavior near the vertical asymptote from the left side, what we can do here is we can now calculate the value at minus 2.1. So when I substitute minus 2.1, I get 5 times minus 2.1 minus 2 over minus 2.1 plus 2. Now in this case, we get both negative. So when you have negative over negative, we end up with positive. That means from this side, it is approaching positive infinity as shown earlier in the graph. So when x is approaching minus 2, from the left side, y is approaching positive infinity. That is a behavior near the vertical asymptote, right? So we are considering vertical asymptote. Now let's talk about end behavior, which is behavior near the horizontal asymptote, right? So when we say end behavior, we are looking at 2 points. When x is approaching minus infinity, what happens to y? And when x approaches positive infinity, what happens to y? That is what we are interested in. Both ways, it is approaching 5, but is it lower than 5 or higher than 5? That is what we are interested in. Correct. So if I substitute a value which is positive high, for example 1000, right, 1000, then in that case denominator is more than numerator, so I get a value which is less than 5. So we are approaching 5 but from below, right? So 5 but from below. But when I substitute negative 1000, in that case numerator is bigger than the denominator, so the value is slightly higher than 5. So in this case y approaches 5 from above, so we say above and below, right? So this is approaching from above and this is approaching from below. Is that correct? When x approaches positive infinity, this is from above. When x approaches negative infinity. So I hope this is absolutely clear. Correct? Now, let's talk about the interval where the function is positive or negative, and the interval for the slope to be positive or negative, or increasing and decreasing. Let's take it on a fresh page. So I'll redraw all this, and then we'll discuss about the function and its slope, right? So we again have the same function here, but let me redraw the graph. So we'll again draw this whole graph and then discuss those things. So what we have here is a horizontal asymptote at y equals to 5, a vertical asymptote which is at x equals to -2. The graph actually goes through like this, right? And this. Some critical points which we found were the y-intercept, which was at -5, the x-intercept, which was at 2. Correct? And we did find a point here which was positive. Perfect. So that is what we have got so far. And now let's once again discuss the behavior near the asymptotes. So as far as the vertical asymptote is concerned, we have already seen that if you're approaching from the left side, the graph approaches positive infinity. If you're approaching from the right side, the graph approaches negative infinity. As far as end behavior is concerned, when x approaches negative infinity, y approaches from above, right? And when x approaches positive infinity, y approaches from below 5, right? The value is 5, correct? So that is what you have got so far. Now, let's look into interval where f of x is positive or negative. Okay, so f of x is the function itself whose graph is before you. So f of x is positive when? You can see clearly it is positive in this left half when it is between -infinity to -2. You cannot include these points. It is also positive after 2, right? So we can write union from 2 to infinity. As far as f of x negative values is concerned, it is negative when it is less than 2 but greater than -2. That is to say between -2 and +2. So that is what you get about the function itself. Now let's talk about the slope. Slope is rate of change of the function. So slope of f of x. Whenever we talk about slope, there are two important things. One is whether slope is positive or negative. Let's look, when is it positive? Positive means that if I draw a tangent, it is rising, correct? So it is rising all the way. So it is positive during this interval, right? Here also, if I draw a slope, it is positive, right? So basically, we see that the slope is positive during its interval. That means the function is always increasing in the interval, and the interval is from -infinity to -2, union -2 to infinity, right? So what we notice is that always increasing in its domain, correct? That's important. Of course, we have a restriction here that x is not equal to -2. So otherwise, x belongs to real numbers. So the domain does not include -2. Otherwise, it is always increasing. Now in the slope, as I was saying, first part is interval when it is positive or negative. It's always positive, never negative, right? So you can also say never negative. Now let's talk about the second parameter, and that is to say increasing and decreasing interval. You can see here that the slope increases from 0 to a large value, right? So we can write this as increasing interval is from minus infinity to minus 2. Now here, it is large positive then negative. So it is not increasing, it is actually decreasing, right? And it is decreasing from minus 2 to infinity. Does make sense to you, right? So I also see increasing and decreasing interval as shape of the curve. You see this is concave up, right? So this shape here is concave up. So this means slope increasing. Now here, this is concave down. And that means slope is decreasing. Does make sense to you, right? So that with concavity, we can easily say whether the slope is increasing or decreasing, right? So that helps. So if you put your arm like this, concave up means increasing, slope is increasing, and if you put it like this, you cannot hold on, it is decreasing. Does make sense to you? So that is how we could also understand increasing and decreasing interval for the rational function. So I hope with this you have completely understood how to describe the characteristics of a rational function like this and how to sketch its graph. So we have 5 critical points here. The horizontal asymptote y equals to 5, vertical asymptote x equals to minus 2, x-intercept at 2, y-intercept at minus 5, increasing decreasing intervals, this critical point which we worked out. Do you see that? So those give you critical parameters to really define the graph and also its characteristics. I hope it makes sense. We'll take up another example on sketching, which will be kind of like this. I'd like you now to sketch the graph of the given function and describe this. We'll discuss how to sketch graph of the function minus 3x plus 12 divided by x squared minus 3x minus 4 in this particular video. Now whenever you're given a rational function, first thing is to factor, right? So let's factor this. We can factor minus 3, and what we get in the numerator is x minus 4, and the denominator, it is a quadratic function. Product of minus 4, sum of minus 3, 4 times 1 can work. So we have x minus 4 times x plus 1, correct? So we have factored it. So that is your first step. So first step will be factor. Now once you factor, it is very easy to see where are the vertical asymptotes and what are the other restrictions. So immediately from here, we can write down the restrictions. Restrictions clearly, denominator cannot be 0, so we have x which is not equal to 4 and also not minus 1. So there are 2 restrictions to this rational function. Now what do these restrictions lead to? Well, you can see that x minus 4 is a common factor and it cancels. Since x minus 4 cancels, clearly we have a hole here. So we can say we have a hole at x equals to 4, since we have a factor in the numerator and denominator which cancels. So once it cancels, we can write this as f of x is equal to minus 3 over x plus 1. Now it is important to find the value of the hole itself. So at 4, what is the value of the function? So it is minus 3 over 4 plus 1, which is minus 3 over 5. So that is the position of the hole. So we have hole at x equals to 4 when y is equal to minus 3 over 5. Clear? So we got one restriction, which is the hole. Here it is a good practice to always write that x is not equal to 4 or minus 1, correct? Okay. Now the other restriction was x equals to minus 1 leads to a vertical asymptote. So we get vertical asymptote at x equals to minus 1, right? So that is the denominator, which will make the denominator 0, right? Now once you have whole and the vertical asymptote, we can now go for horizontal asymptote. Since we have minus 3 over x plus 1, denominator is very high. When x is very high, it leads to 0. So horizontal asymptote is y equals to 0. Correct? So we have the basic structure for the rational function. Now I'll sketch this here. We have a vertical asymptote which is at x equals to minus 1. So let me draw this here. Right? We have a horizontal asymptote which is y equals to 0. And we also know that there is a hole at x equals to 4, y equals to minus 3 over 5. Right? So let's say this point here represents the hole. Correct? Whose position here is x is 4 and y is minus 3 over 5. Clear? So that becomes the framework around which we are now going to work. The other critical points are very easy to take out. One is the x and y intercepts. Now in this particular case, the numerator is minus 3, right? So we have no x-intercept. However, we have a y-intercept. Y-intercept is the value of the function when x is 0. When you substitute 0, we get minus 3. So the y-intercept is at minus 3, right? So this value, minus 3, becomes the y-intercept, right? So connecting these points, we know the graph should be kind of like this. Now on this side, we are not very sure how will it look like. Well, we know this is your vertical asymptote at x equals to minus 1. So we can take a value at x equals to minus 2 and see what is going to be the value of the function. So let's calculate the value of the function at minus 2. We'll use the simplified equation, which is minus 3 over minus 2 plus 1. And that gives you minus 3 over minus 1, or it is equal to 3. So at x equals to minus 2, we get a positive value. And the positive value is plus 3. Okay. So that means that clearly this part of the graph should be like this. Well, this point here is minus 2 plus 3. Is that clear? Right? So that is how we actually get the sketch of our function. And now we can actually describe the characteristics. Let's begin with the end behavior, which says when x approaches negative infinity, we know y approaches 0. But does it approach from top or from bottom? Well, we can substitute a large negative value in this. So when I substitute a large negative value, I get a positive value. So it means from above, right? And when x approaches positive infinity, y approaches 0. When I substitute a positive large value, I get a negative value. So it is from below. Do you see that? So clear. Now, behavior near the vertical asymptote. When x approaches, vertical asymptote is at x equals to minus 1. So when x approaches minus 1, from the right side, we write like plus. In that case, y approaches what? So I can actually write a value minus 0.9, for example, in the given expression. And what we get here, when we write minus 0.9, numerator is negative, but denominator is positive. So we get a negative infinity. And when x approaches minus 1 from the left side, we see that the y value approaches positive infinity. So that is the behavior near the vertical asymptote, right? So I hope that is absolutely clear. Now, once you have defined all these behaviors, then we have more or less described all the characteristics. We can now say that the function f of x is actually greater than 0 in the interval from minus infinity to minus 1. And f of x is less than 0, or it is negative in the interval from, so there is a split here, do you see that? So this point is not in the domain. So when you're describing this, you have to say from minus 1 to 4, union from 4 to infinity. Do you see that? That's kind of important. Now, let's talk about slope. Now, slope is the tangent on the curve. It is rising. Do you see? So slope is positive or increasing for x belongs to real numbers where x is not equal to minus 1 and 4. You could write like this also. Now slope could be also, what about the rate of change of slope, right? So rate of slope. Now let's talk about rate of slope. Now this portion is concave up, so it is positive. So it is positive or increasing, positive or increasing. Increasing is better word, not right positive. Increasing in the interval from minus infinity to minus 1. This is concave down, right? So it is decreasing from minus 1 to 4, right? And then from 4 to infinity, since it is concave down. So using the property of concave up and concave down, you can easily comment on the rate of change of slope. Is that clear to you, right? You can also say the graph of the function is concave up in this position from minus infinity to minus 1. Let me write down concave up. And in this portion, it is concave down. That explains the rate of change of slope. So whenever it is concave down, the rate of change of slope is decreasing, right? And when it is concave up, the rate of change of slope is increasing. So I hope with this, you understand how to completely describe a rational function and sketch its graph. Hope it makes sense. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.